So we're going to talk about this ARS in AI/ML workload. Um, so, so since the introduction of this cloud computing, I think those hyperscale networking has been building these cloud networks for a decade now, and we are using our traditional routing and the switching techniques in those hyperscale networking. However, I'm trying to convince you in the next few slides that with this, the new workload introduction, the AI and ML workload introduction, we do need some new development in new routing schemes in order to address those challenges. And you guys have heard about various perspectives in terms of monitorings, in terms of congestion controls, how to deliver a low latency network in those hyperscale network. Now, today's topic, I'm going to talk about something that is dear to every networking people's heart, is this routing. Can we do something in routing to deliver the low latency network? So first, I'm going to explain a little bit about what is ARS. So ARS is adaptive routing and switching. It means that the router and switches can really forward the data, to a different route based on the current condition of the communication circuit within a system. That's from the Wikipedia. What this means is that, based on my local information, some other like traffic load and queuing and other information, I can adaptively adjust to the current network load and then change to route packet to a different path. And why? So next, we're going to cover why we need that, and happy to discuss. Jay is going to discuss our new initiative to support these efforts in the site community. We're really bringing these efforts into site community so that we can enable this across all the site. The ASIC that supports the site. I'm a networking guy. I'm not really a AI guy. I'm a guy, so can read those your slides. But what really I know is that in this kind of workload, there's a lot of traffic to be exchanged across the different learning nodes, and it really pushing the network load to the edge, which means that when we say the application requires a high network utilization, we not mean like 50% of utilization or 60%. We're talking about near 90% of utilization or even 95% of utilization. And under that kind of a stress, we still want to deliver a low latency network to our applications so that they can run their training, their inference much faster, right? So that's the challenges that nowadays, we're facing in terms of delivering that kind of infrastructure to the application. And so how we're doing now? I mean, in the cloud network, right? So basically, I think it can be, there are a few things that we're doing right now. Is that we're doing the routing. We advertise those reachability informations across different nodes. So the path selection by the routing, right? So and then in some cases, we heard about traffic engineering. So in some special cases, we adapt to that workload, and then we create some provisioned paths, either using MPS, using whatever tunneling techniques to do the traffic engineering. That's something that we also do. But most frequently, we're leveraging this ECMP feature to do the load balancing across the different equal cross path lengths. And that is the main technique we're using to distribute load so that I can leverage those parallel paths in this network. However, the challenge is that at the low-level link utilization, it's not a problem because when we do the ECMP, we are using the hash functions because we want to keep every flow to be pinged on an exact path because we want to avoid those reordering some of those flows. However, such static hash allocation does create collisions among those flows. So imagine you have a very big flow, 100 gig or 400 gig, that over the network it transfer over one pass. But you have other flows, small flows, or even another big flow that happen to have the same hash value being generated and collide with this exact same flow. Then, while your network still have bandwidth, overall the bandwidth in your parallel links, but still on this particular link, you have two large flows that been collided, and they were suffered. They cannot really, our network cannot really offer them the free bandwidth that we still have, right? So that's a problem. I think when the link utilization grows to 95, or even higher utilization, and also, in some cases, when the network is huge, we'll have failures. We have link failures. We have CRC errors across our network. Then in those cases, we need to bring link down. And currently, the reaction time is through the control plan, which is a lot more slower than what we're going to talk about in a few slides. And I think the static hashing is the same, for both ECMP and lag. People are well understood. I hope I can convince you that yes, we did need a new scheme for the routing.
Thank you, Guohan. Yeah, so I really hope that you got to a certain level of conviction that yes, we need this, but 20 minutes is not enough time to convince you. Neither it's enough time for me to go over the entire content. I'll do my best. So just to recap, today, forwarding paths are being laid out by the control plane. Protocols learn the reachability information. They get redundant paths, and they create the ECMP, and then those paths are programmed in the hardware. At the most, what hardware does today is does the load balancing based on the static hash. And as Guohan pointed out, that's not efficient. So what we are trying to do is we are trying to build intelligence in the hardware, where hardware keeps certain information, maintains certain state, and then takes a runtime decision. And that decision is at a granularity of nanoseconds, could be at a granularity of microseconds, depends on the deployment and the workload. And then based on that information, it takes a decision that, okay, this link or path is degraded based on this matrix, and I'm going to take an alternate path. So what I'm going to do is go detail into this concept where a path is chosen based on a matrix, which is being learned dynamically by the hardware. It's a big topic, but I'll try to cover as much as possible. So as I was saying that, the slide did not change. Slide is not changing. Okay. Yeah. So adaptive routing basically introduces a concept where the quality of the link is maintained and the path selection is done based on the link quality. And the quality measure is both, which is the past and the future, right? So in a link, I'll clarify what past and future means. The following slides cover it, but just for the clarity's sake, you're like, how do you know your future, right? So past is on a link is the experienced load, which is the number of bytes which we keep as a counters, right? Gone over a given time interval. So that's your load, right? Or a bandwidth utilization. And the future load is the amount of traffic which is sitting onto the queues which are being linked onto that port. That queue traffic, queue traffic, is still not the load experienced by the port, by the link. That is your future load. So you have a past load, which is the bandwidth or the load as experienced by the link. There's a future load, which is the amount of traffic sitting into the queues, which are assigned to the port. So based on this, the path assignment is done. So before I go in detail, there are certain acronyms you will see in the presentation which are being referred again and again, and I want to clarify it. So for this topic, we have introduced certain notions which are probably may not be industry standard, but let's go with it. So microflow is nothing but a 5-tuple flow. So just for this conversation, when I say microflow is nothing but just a 5-tuple flow. Macroflows is a collection of microflows. So think about it, multiple flows which they hash to the same value. That hash bucket is basically carrying macroflows. Flowlet is the sequence of packets within a macro flow which are being separated by some time interval, okay, and that time interval is configurable. So we will refer it to as a flowlet. And as I was saying, that the decision is done by the hardware. So hardware has to maintain some state. And that state is maintained in the macro flow table, which is at a granularity of a flowlet. So hardware maintains a state which is at a level of flowlet. And the forwarding decision, which I'll come to the next slide. So this I already talked about. The matrix, the quality measure which is maintained is the link load, which is the past load, in-flight load, which is the future load, which is the queue TX byte count, which is sitting into the queues. And the idea is that not necessarily we have to take the decision at a macro flow level. Sometimes decision has to be done at a micro flow level. And the simple use case is if there's an elephant flow, long-lived flow, which is going through the system, you want the decision to happen at the micro flow level, at that 5-tuple level. So as far as the adaptive routing is concerned, it should work at a macro flow level and a micro flow level. So that's what the bullet is saying. Finally, it's possible that even though we have done this concept of dynamic path assignment, there is a case where we are not able to tune the interval, the time interval. You can make an argument that there is elephant flow, which is really back-to-back. There is no idle time. So how do you define a flowlet? When you don't define a flowlet, then we introduce a concept of a minimal and non-minimal cost paths. Basically, we are saying that if an elephant flow is going to a path, eventually that path is going to degrade, right? Eventually something is going to happen, it's going to take more load. And when that path degrades, then we should have an ability to change the path to a non-minimal cost path. And that's what the bullet says. Finally, the path assignment is done at 2 stages. One is when the flow starts for the very first time, the beginning of time, right? So that's when the path assignment is done. Other time, path assignment is done when there's a concept of flowlet is introduced. So if you see in this concept, the path assignment is being done extremely aggressive. So some million of packets goes, there's the idle time, and then we again see, is this the current path, the best path available? If it's not, then we do the reassignment. And finally, in this case, the other thing which I forgot to talk about is the link failure. So today, as Guohan was mentioning, when the link goes down, the reconfiguration of the ECMP buckets, there is a control plane involvement in that. You may have a FRR enabled, which does the fast detection. You may have a BFD enabled. But eventually, some control plane interaction is there, which has to reprogram the hardware. In this case, the link failure is detected within the hardware. And once the link failure is detected, essentially the flows which are going through that path, the flowlet, will be reassigned a new path. So whenever there's a link failure happens, all the flowlets which are going through that link will automatically reassign to the new path. So in this case, there is almost minimal drops you will see, definitely no black holing, and convergence time is in the terms of very low microseconds. This I already talked about, the primary and alternate path. This is mainly to address the elephant flows when there are flows which are long-lived and there is no concept of idle time. And in that case, we we want to have some concept where the path has degraded, the link has degraded, and we want to take a non-minimal cost path. So in this case, we introduce a concept of primary and alternate paths. So you can have adaptive routing and switching configured. Besides that, you may also have a concept of primary and alternate paths, and that is when the flows are observing no idle timeouts. So in that case, there's other scheme which is going to kick in, and that scheme is going to choose the non-minimal cost paths. Path selection, I'm a little bit rushing because we are out of time. Path selection is done based on many criteria. The most common is the flowlet based. The most aggressive is the per packet based, which essentially looks like per packet load balancing, except it's not a static load balancing, it's a dynamic load balancing. The path selection is done based on the dynamic conditions of the network. The other one is the fixed one. Fixed one is mostly used for debugging. When the deployment has happened, you want to see how the given configuration is working. In that case, you can do a fixed assignment, see how the network is behaving, and then change the modes. So there are various stages within the adaptive routing and switching concept. These stages are conceptual stage. Don't think that they are actual hardware stages. And the reason I'm presenting them as a conceptual stage, because eventually our goal is to present these stages into the SI pipeline. So the first thing which we want to know in the adaptive routing is the participating links. What all links are participating in the adaptive routing. So you can have a deployment where segment of the network is not participating in ARS and segment of the network is participating in the ARS. And that could be because a pod is partitioned into a storage or some other kind of deployment. So we have to figure out what links are participating, and since links are of different speed, we have to normalize them. So there's a scaling factor which we have to introduce for a link speed so that when the measures are done, they are normalized to a consistent baseline. Weight assignment. So this is for a given workload. Is the past load of critical nature or is the future load of critical nature? So you can assign a weight and say, you can say, my future load is of more importance to me. Past load, I have other means to measure it. Data collection. The way we compute the matrix within the hardware is based on data collection. So you have to enable some kind of sampling in that. Quality metrics, there's an algorithm running in the hardware. Algorithm, what we are running today, I'm from Broadcom, so Broadcom switches, is the EWMA, which is exponentially weighted moving average. And if you take the EWMA algorithm and then use the information available, it's a real number. It's a very large space to operate. So what we do, we quantize it. And once we quantize it, then we use the quantized information into the hardware. So same thing is for SI. We have to specify what is the algorithm we want to use, what are the parameters for the algorithm. It uses various parameters. What kind of quantization we want to do. Is it a float quantization? Is it buckets with a range? What kind of quantization? And then the bands, the mapping of that quantized buckets onto the decisions. Bucket 0 means the best path, bucket n means the worst path, things like that. And finally, the table, which is the table maintaining the state. So this is a conceptual packet flow. So in this case, I have tried to abstract the way packet is going to flow and go through the pipeline to give you an idea that how this technology is going to work. So initially, the flows are coming, the packets are coming, and they're identified by 5 tuple. So that's what your microflow 1, 2, and 3 is there. They go through a hash, okay? And hash maps them into a bucket, okay? And that bucket, where it's mapping, is where you configure the idle timeout. You say that flows which are going into this bucket, now which becomes a macro flow, if they are separated by this idle time, t, then this is my flowlet. So in this diagram, you see there's a flowlet 1, 2, and 3, and they are composed of different microflows, different 5-tuple flows. Now, decision is based at a per flowlet level. At a flowlet level, there is a hardware engine which is computing the matrix, the quality, right? And then the flow table takes a decision that from all the available paths, what is the best path available for me? And that decision, based on that decision, flowlet 1 is assigned to a path. Then the next flowlet comes through, and it again takes that decision, right? And it's quite possible that macro flow 1 will get aged out. There won't be anything left for that hash value. And then some other flow will come and take that space. So that's a conceptual diagram where there are 4 active participating links. They are being monitored for a link quality. They are being mapped onto a link quality matrix, which you see as a green, blue, orange, and so on and so forth. And the path selection, which happens based on the available paths, which are configured as adaptive routing ECMP groups, is essentially nothing but the hardware table. And dynamically, based on a quality, A, B, C, or D path is selected. So that's kind of a very high-level view. We are going over time. I knew that. So, so I'm going to stop here. Just give, it's a very big conversation. So I'm going to stop here and ask if there are any questions.
Yeah, one question.
One question.
I know this is a very exciting topic. There are probably like 5 questions, but we'll take one question.
So, so there is always some debate on how networks should only passively provide information and allow the end host to do action, right? Versus you allow network to do action based on the load. So can you please comment on this? For example, I can give an example. If the one particular link has a partial failure, have a packet loss, right? So if the packet can only go one pass, application can detect a loss and switch different paths. But in your case, if your traffic actually being spread on multiple paths, there's no point for you to detect which paths actually have the partial loss, partial failure, and even application start new connection would not avoid this scenario.
Yeah, so I think if I place the question a little bit differently, there is a conflicting concept when we talk about HBCC. It relies on the state of the network, which is a deterministic state, what path, what queue, where the packet is going. In this case, since the path and the queue information may change dynamically, right? How does the end application work in this case, right? And you can argue that one is better than others. But point taken, I don't have a good answer for it. I accept your argument.